Diaz, and today we'll be covering Chapter 2 of Psychology of Work, which talks about research methods. These are the methods that IO psychologists use in their research. The first thing we'll discuss is the research process. The research process is very important as it always follows the same 3 steps. The first step is to review past theory and research that are related to your topic. The second step is to describe your own study methods and results. And finally, to conclude with implications for practice, theory, and future research. Basically, step 1 is to look back, step 2 is to describe what you did yourself, and step 3 is to look forward. A theory is the description of the relationships among variables and how these variables influence each other in order to explain a particular phenomenon. It sounds very difficult, but it's basically what you've always known a theory to be. It describes how things work together. It's very important to understand the impact that theory, research, and practice have on each other. In order to understand this cycle, we're going to discuss the example of genes passes. A genes pass is a motivational tool that employers often use to motivate their employees. They give them genes passes, which allow them to wear jeans instead of their normal work uniform or dress code. In this example, let's start with a theory. Perhaps the theory is that using genes passes will result in happier employees. So I might conduct some research to test this theory. Perhaps my research confirms my theory that genes passes do result in happier employees. So this will affect practice. More employers will use genes passes because the research tells them it's a good idea. When more employers use genes passes, that may result in more theories. Perhaps they find that genes passes only work when they're strongly tied to work performance. This theory will result in further research, which will change things in further practice, which will then lead to new theories, new research, and more changes in practice. As you can see, this is a never-ending cycle. Another important distinction in research is the difference between the deductive approach and the inductive approach. The deductive approach to research starts with a theory and sets out to test the theory, whereas the inductive approach starts with an observation and develops those observations into a theory. Let's look at a diagram to understand this a little better. Deduction starts at the top with a theory. If you'll notice, the arrows go down from theory to hypothesis, then observation, and finally a confirmation. Aristotle is a good example of somebody who conducted deductive research. He would start with a theory and set out to test his theory through experimentation. Induction, however, starts at the bottom. If you notice on the orange side, the arrows are pointing up. We start at the bottom with an observation, notice patterns through those observations, which lead us to a hypothesis and eventually a theory. Sherlock Holmes is a good example of somebody who would use his observations to eventually create a theory. Now let's talk about what exactly an experiment is. It's very important to be able to identify an experiment since only true experiments can be used to study cause and effect. The key features of a true experiment are that it uses an experimental group, a group of people who receive the manipulation or the treatment or the training, a control group, a group of people who do not receive the manipulation or the treatment or the training. They get nothing, and they're used for comparison. And finally, a true experiment involves random assignment of the participants to these experimental and control groups. This ensures that there's equivalence between the groups. For example, we wouldn't want to put only men in the group of people who get to use a genes pass and only women in the group of people who don't get a genes pass, because then if we found that the genes pass group was happier, we wouldn't know if it was because of the genes pass or because of their gender differences. There are 2 types of true experiments: Since both are experiments, they can both be used to look at cause and effect, to study cause and effect, but they're done in different places. A field experiment is done in the field. In organizational psychology, the field is the workplace. This is the gold standard, the best way to evaluate the effects of workplace policy or intervention or training because we actually study it in the real world, in the workplace. However, there's several limitations to field experiments. For one, they can be quite difficult to carry out. They require that the organization is willing and able to assign workers to different conditions. And finally, some manipulations might be unethical or illegal in the workplace. For example, if we wanted to study the effects of hunger on workplace productivity, we might want to deny the control group their lunch break. But as you can imagine, this would be both unethical and illegal. On the right-hand side, we discuss experiments conducted in a laboratory or online, which are both called lab experiments. Laboratory experiments typically involve college students or large online samples. They're very cost-effective, time-effective, easy to do. However, the main limitation is it may not be generalizable or transferable to the real world since it happened in a laboratory, not in the real world. Again, both of these are true experiments and have pros and cons. And since they're both true experiments, they can both be used to study cause and effect. When we're studying cause and effect, what we are looking at is variables. And in fact, we have an independent and a dependent variable. But first, let's talk about what a variable is. A variable is something that can change or vary. In math, when letters represent numbers, like in algebra, we call it a variable because the number can vary. In data collection and processing, we always look at two or more variables. For example, does height affect basketball skill? Does gender affect height? You may have noticed that in general, males are taller than females. Does location affect water fountain usage? If you go around your workplace, you may notice some water fountains or filling stations are used more than others. Perhaps this is because of their location. So what's the difference between an independent variable and a dependent variable? The independent variable is the cause, and the dependent is the effect. The independent variable comes first, and the dependent comes after. The independent happens by itself, whereas the dependent happens because of the independent one. And finally, the independent variable, when we're graphing, goes on the x-axis, and the dependent goes on the y-axis, the vertical axis. In an experiment, you can control the independent variable, and then you measure the dependent variable. If we go back real quick to our last slide, if we were trying to study the effect of height on basketball skill, height is independent. We cannot change the height of our participants, but we would look at their height, which happens anyway, and then measure how it affects their basketball skill. Are the taller people better basketball players than the shorter people? Let's look at a few more examples of independent and dependent variables because it's quite important to know the difference. Our first example compares the price of eggs to how many eggs you can afford. As you can imagine, the number of eggs you can afford depends on the price of the eggs, meaning that the price of eggs is the independent variable. That happens no matter what. And the number of eggs you can afford depends on the price of the eggs. The second example compares grades versus time spent studying. Your grades depend on the amount of time you spent studying. So the time spent studying is your independent variable and the grades are the dependent variable. The time to complete a puzzle also depends on the number of pieces in the puzzle. It wouldn't make sense to say the number of pieces in the puzzle depend on how long it took you to complete it. The puzzle had a certain number of pieces regardless, but the time it takes you to complete it depends on how many pieces there are. Finally, the price of your car insurance depends on how many accidents you've had. The accidents are the independent variable. That happens on its own. The price of your car insurance depends on the number of accidents, making price the dependent variable. I know this can be a little confusing, so feel free to reach out by email if you would like some more practice or clarification on independent and dependent variables. A quasi-experimental design, as you can imagine, is almost an experimental design. It's similar to an experiment, but sometimes just missing one of the important things, like maybe random assignment to the two groups. These can be very practical in a field setting. For example, I could find an organization that already uses genes passes and an organization that already does not use genes passes and compare those two. We don't have random assignment in this case, but we do have a control group and an experimental group, and their data is still valuable. This slide has a lot of information, so let's take some time to unpack it. It talks about types of data collection. So when you're doing the experiment, or when the researchers are doing the experiment, how do they get their data? There are three main ways to collect data for an experiment. One is with a survey, the second is by observation, and the third is by looking at archives. Survey methods involve people reporting their responses on paper or online in a questionnaire or survey. This is the most frequently used method of data collection in IO research. It usually uses pre-established survey items or scales and can collect large amounts of data from many participants. Survey data is also fairly easy to analyze because it comes in numerically. It comes in numbers, so we can run the statistics right away. The downside of survey methods is that they don't always provide the richest data available. Not always detailed enough, individualized, and it doesn't always include issues that the original researchers didn't consider. Next, we'll talk about observational methods. This is when we observe things to collect our data. Observation can be conducted in the field or the workplace, which makes it very valuable. It can provide richer data than a survey, since you're right there in the workplace watching it with your own eyes. However, data from observations has to be coded to run the statistics. Because you're writing down words that you're observing, those then have to be converted into numbers in order to do some statistical analyses. The other problem with observational methods is that they're time-consuming and usually involve smaller number of participants. Finally, archival methods involve analyzing old records or government data. It's cheap and easy to use big samples. However, the data was not collected with the specific research question in mind, and sometimes this data can be outdated because it's old. Only data collected using the experimental method can look at cause and effect, however. Let's look at the picture real quick. We see a researcher using naturalistic observation. She's using the observational methods to observe the kids playing in the sandbox. Next to that is a picture of a researcher sitting at a table having some students fill out a survey using the survey method. And finally, we see a researcher looking at old records to use the archival method. All of these will allow us to look at cause and effect as long as they're part of a true experiment. Now we'll talk about correlational studies. The most important thing to remember about these kinds of studies, correlational studies, is they do not determine cause and effect. These are different than an experiment, and they do not allow us to look at cause and effect. There is no independent and dependent variable because we don't know what causes what. However, what a correlational study does tell us is how highly related different things are to each other. The advantages of a correlational study is they can be done in organizations using samples of actual working people. We can collect the data without having to manipulate anything. We just observe and mark it down. Typically, it's practical and cheap to do and can be done using surveys. However, the downside of correlation, like I mentioned, is you can't use it to determine causality. It doesn't tell you which variable causes the other one. For example, perhaps we find that employees who are more productive are also more tired. We don't, or are also more tired, sure. But we don't know if their high productivity levels cause them being tired or not. We just know that they're related. Let's look at some R values for correlation. The R value tells us both the direction of the correlation, positive or negative, and the level of the correlation, if it's a strong correlation, a moderate correlation, or a weak correlation. In our first graph, we can see the dots line up pretty nicely on that blue line there. They're moving upwards, meaning that it has a strong positive correlation. The R value for this correlation is 0.92. That's a very high correlation and it's positive. This means as one variable goes up, the other one does too. Maybe these researchers were looking at levels of depression and number of divorces. We can see that people who have a lot of divorces, who've been divorced several times, are more likely to be more depressed. And people who have not gotten divorced are less likely to be depressed. However, we don't know what causes what. Did the divorce cause the depression, or did the depression cause the divorce? We don't know. We just know that they're related. In the top middle, we see a weak positive correlation. Perhaps we're comparing time spent studying to grades. We see that the more somebody studies, the higher their grades are, but perhaps the better students study more. We don't know which causes which in this case because it's a correlation. We also see that they're not always completely correlated. Not everybody with high grades studied a lot, and not everyone who studied a lot got high grades. In our third example, the R value is negative 0.92. It's still a very strong correlation at 0.92. This time it's negative, meaning as one variable goes up, the other goes down. Perhaps these researchers were looking at depression and number of pets. People with more pets are less depressed, and people with less pets are more depressed, but it doesn't mean that the number of pets causes the depression or that depression causes you to not have pets. It just means that they're related, and they're negatively related, meaning as one goes up, the other goes down. On the bottom row, we see a weak negative correlation and a moderate negative correlation. Again, these are negative because as one thing goes up, the other goes down. But the bigger the number is, the stronger the correlation is. Finally, we have a 0.04 correlation, or 0.04 R value. That means no correlation. These two variables are not related to each other. Perhaps these researchers were looking at the length of people's hair and the size of their feet. What they found is people with long hair are no more likely to have big feet or small feet, and people with big feet are no more likely to have long hair or short hair. These variables are not related, so there's no correlation at all. Linear regression is a model that we use so that correlation can actually be used to make predictions. In this graph, we see that job satisfaction and job performance are related to each other. They have a fairly high R value of positive 0.81. Positive meaning that as one goes up, the other goes up, and the 0.81 means there's a fairly strong correlation here. However, since it's a correlation, we don't know which one causes the other. We see that high job satisfaction is related to high job performance, and low job satisfaction is related to low job performance. But does the satisfaction result in their performance, or does their performance affect their satisfaction? That we don't know since it's a correlation. However, we can use a line to make predictions. The graph on the bottom right shows the cost per units of electricity. This is not a correlational graph. This is a linear graph. As the units of electricity increases, the cost increases, and they increase at the same rate. We can use this line to make a prediction. If I wanted to know the cost for using 1,000 units of electricity, I could continue my graph and figure it out. Back to our correlational graph on the left, we draw that line through the middle of the red dots to allow us to make predictions. I can now take an employee's job satisfaction score and use it to predict their job performance. I can also look at their job performance and use it to predict their job satisfaction. So a linear regression line allows us to use correlational data to make predictions. Remember, there's still no direction of cause and effect, but we can make predictions. Now we'll talk about statistics a little bit. Don't worry, we don't have to do any math. We're just going to talk about the difference between mean, median, and mode, which are all ways of describing data. The mean is the mathematical average of a set of numbers. Generally, when we talk about average, we are discussing the mean. If you figure out your average grade in this class, what you'll be calculating is your mean grade. To calculate mean, you add up all the numbers and divide by how many there are. If you wanted to know your mean on your quizzes, you would add up all your quiz scores, and if you've taken 5 quizzes, you would divide that by 5. I put a mean face next to mean because it helps me to remember that the mean is the one that makes you do all that mean math to figure it out. Next, we have median. I put a picture of a median road sign. The median is the strip of grass or cement in the middle of the road between the 2 directions of traffic. The reason I put that is to remind us that the median goes in the middle. And in statistics, the median is the midpoint of the data set. To find the median, you put all your numbers in order and just take the middle number. Finally, the mode is the most popular number. I put a piece of apple pie a la mode, since it's the most popular kind of pie in America, to remind us that the mode is the most popular score. If I want to find the mode, I'll put all my data in order and simply look for the score that appears the most often. There can be more than one mode. Over on the right-hand side are the definitions for range and standard deviation. The range is simply the largest value in your data set minus the smallest value. For example, if I wanted to know the age range in this class, I would take the age of the oldest student and subtract the age of the youngest student to see the age range. A range in a class like this would likely be a lot larger than the age range in, say, a second grade class, which would probably be less than 1 year. Finally, standard deviation tells us how much the scores vary around the mean. So if I tell you the average age in this class, the mean is 30, our standard deviation will tell us if most people are right around 30, most people are within their 20s and 30s, or if there's a large standard deviation, this would tell us we have many older people and many younger people, a lot of variability in our scores. A t-test is an even more complicated type of statistic, and this allows us to determine whether there's a significant difference between 2 means. In this example, we had a control group who received no training at all, and a trained group who was trained in the classroom. As you can see, the trained group scored higher than the control group, but the question is, was it significant? Was it high enough to be important, to tell us that that training had an effect? Conducting a t-test will answer this. It will tell us either, yes, these means are statistically significant, the difference is statistically significant, meaning that the classroom training had an effect, or no, there's no significant difference, meaning the classroom training did not have an effect. Sometimes we have more than 2 means to compare, so we use what's called an ANOVA, analysis of variance. Another word for an ANOVA is an F-test. The F-test compares 3 or more means all together. It tells us if there's a significant difference amongst these means. In this example, we have a control group who received no training at all, one trained group who was trained in the classroom, and a second trained group who was trained online. We want to look at the differences between all 3 of these groups. If the F-test shows that there is a significant difference between these means, we can then conduct pairwise t-tests to see where those differences lie. So, If my F-test tells me, yes, there is a significant difference amongst these means, I will then conduct t-tests between control group and class trained, control group and online trained, and class trained and online trained. Every pair will be analyzed to see where those differences are. Maybe the difference is just between general training and not training. Or maybe the difference is that online training is better than classroom training. We'll find this out using pairwise t-tests. Just a couple more things and we'll go on to our summary. When you're using a survey to collect data, or even sometimes observation, we use different types of measurement scales. A nominal measurement scale simply classifies people into categories. It doesn't use numbers. You would answer male or female, or you might answer with your job title or what city you come from. These are words, not numbers, and they're considered nominal scales. An ordinal scale can use a number or a position, but it's not a meaningful interval. For example, if somebody comes in first place in a race and somebody comes in second place in the race, we don't know how far behind the second place runner was. We just know that they came in second. Also, there may be a difference between the first and second place and the second and third place. Maybe the second place runner came in just a second after the first place runner, but the third place guy came in 10 minutes later. We don't know, we only know their rank. This is called an ordinal scale. On the right-hand side, we discuss interval scales, which do have a meaningful difference between numbers. They're spaced out equally, the numbers. However, there's no absolute zero. The numbers are not true values. They're more like ratings on a scale. Finally, a ratio scale uses real numbers with a real absolute value. Examples of a ratio scale would be asking you your income or how many items you can produce in an hour. This is a meaningful number based on an absolute zero value. Now we're going to discuss reliability and validity of measures. Measures are what we use, surveys or observational measures or archival measures, anything we use in our research. But before we use a measure, it's important to know that it's reliable and valid. So let's discuss the difference. The little picture on the left, you see the man scratching his head trying to figure out which is more important, and the answer is both are equally important. Reliability makes sure that our results are consistent, whereas validity makes sure that our results satisfy our objectives. Is it measuring what we really want it to? So reliability asks the question, does the measure yield accurate results? And validity asks the question, is the measure actually measuring what it's intended to? Let's look at the target diagram to understand this a little better. In the first target, A, we can see the shots are not valid or reliable because they didn't hit the bullseye like we wanted them to, nor did they hit the same spot every time. In target B, we see that they did hit the bullseye, or the center circle, but it didn't hit the exact same spot every time. So they were valid shots. It hit where we wanted it to hit, but they were not reliable shots. They weren't the same every time. In target C, we do have reliability, but not validity. This time they were consistent, but not valid. They didn't go in the middle like we wanted them to. Finally, in target D, we have valid and reliable results. This person shot their dart at the middle where it was supposed to go, and they hit the same spot every time, making it reliable. Let's talk about two different kinds of reliability, then we'll talk about validity. We're almost done, I promise. Test-retest reliability is using the same measure, the same survey, or the same type of measurement, but on different days to see if it's reliable. If you look at the chart, the table on the left, you can see that Sally took measure A 2 different times, same measure, different days. And she scored almost the same. She got 78 the first time she took the survey and 79 the second time she took it. Susan's score changed very minimally from 62 to 59, and John's score stayed exactly the same. Overall, there was a correlation of 0.99 between the two times. This shows very high test-retest reliability. This shows that it's a good measure. Even when I give it to people on different days, their scores stay the same. However, the table on the right shows low test-retest reliability. In this case, our first participant's score went down from 56 to 40, whereas our second participants went up from 30 all the way to 63. Overall, the correlation was only 0.51, meaning it's not a very good test. It doesn't have high test-retest reliability. These people took the same survey on 2 different days and got very different results. That's low reliability, not consistent. Another type of reliability is inter-rater reliability. This, again, uses the same measure, but instead of giving it on different days, it's given by different researchers. So Jim took the same survey twice, once with researcher A and once with researcher B, and as you can see, his results were quite similar, 78 and 79. Doug also took the same survey twice with 2 different researchers, and his scores were similar as well, 62 and 59. Francis's scores stayed exactly the same no matter who gave him the survey. So we can see that this measure or survey has high inter-rater reliability. No matter who gives it, no matter who does it, people score about the same. So our results are consistent. They're reliable. To talk about validity, remember validity asks whether our measure is measuring what it's supposed to be. To talk about validity, let's use the example of the SATs. There are 3 types of validity. The first is content validity. The measure has to include all areas of the domain, which means in our example of the SAT, if what we're trying to study is academic success or academic ability, we don't only want to ask math questions. We don't only want to ask language arts questions. We want to ask a little bit of every subject, cover all areas of the domain. Second is criterion validity. This asks, does the measure have a relationship with a related outcome? What should the SAT be related to? Maybe success in school or high grades in college. So we look and we see, do high SAT scores correlate to high grades in college? Or do high SAT scores correlate to high intelligence? We want to see if it has a relationship with an outcome, with something that comes out of it. And finally, there's convergent and divergent validity. This makes sure we're measuring the right thing by comparing our measure to other measures. In this example, we can compare the SAT to something that's supposed to be related to it, perhaps the ACT test. Do students who score high on the SAT also score high on the ACT? If so, it has convergent validity. But it also needs to have divergent validity, showing that this measure does not have a relationship with things it should not be related to. For example, is the SAT related to your athletic abilities? If it is, that could be a problem because we're not supposed to be measuring athletic ability, we're measuring academic abilities. So convergent validity checks if our measure is related to things it should be related to, and divergent validity makes sure our measure is not related to things that it should not be related to. Overall, validity tells us whether or not our measure is measuring what it's supposed to be. The last thing we're going to discuss today is ethical issues in research. Informed consent is what ensures that the individuals understand what they're doing when they take part in your research. All the participants need to understand the risks and benefits of the study, and their participation has to be voluntary. They can't be forced to do this. Informed consent is the most important part of the ethical procedure, but to make sure that all academic institutions, all schools and universities who are conducting research follow the rules properly, they created something called the IRB, the Institutional Review Board. The IRB is an institution that basically governs the research process at schools, at academic institutions. So before you were to conduct any research through a school, you would need IRB approval. Outside of academic settings, there's other codes of ethics that IO psychologists can follow, but most research is done in an academic setting, so it needs to be approved by the IRB. I'll give you a moment to look at these comics that I found about the IRB. As you can see, researchers are not big fans of the IRB, but it really is a necessary evil. It can be a pain in the neck to try and jump through all the hoops and fill out all the forms needed for IRB approval, but it's important to have IRB approval to make sure that the study is ethical and that all the participants are being treated ethically. All right, that is it for Chapter 2. Let's go over the chapter summary together. These chapter summaries are really important because they will prepare you for your quizzes and your exams. So make sure you pay attention during the chapter summary. Perhaps watch it a few times. The research process has 3 main steps. The first is to review previous research, then conduct your own, and finally, describe implications for future research. The deductive approach to research starts with a theory and leads to observation, whereas the inductive approach to research starts with an observation and leads to a theory. Remember, the inductive approach is the Sherlock Holmes way of doing things. First he observes, then he creates the theory. An experiment is the only thing that allows you to study cause and effect. And true experiments have an experimental group, a control group, and random assignment to these groups. Experiments can be conducted in the field, which is best but difficult, or in the laboratory, which is still good and much easier and cheaper. The independent variable affects the dependent variable. Remember, these are only present in an experiment, independent and dependent variables. Data for experiments or other kinds of research can be collected using surveys, observation, or archival information, old data. Correlation measures how much 2 variables are related. However, correlation does not tell us about cause and effect. When doing correlational studies, we calculate R values to tell us how closely related variables are. An R value close to +1 or -1 means that the variables are strongly correlated. A positive correlation means that as one variable increases, so does the other, whereas a negative correlation means that as one variable increases, the other decreases. But remember, with correlation, we don't know which one causes the other. A linear regression line allows us to make predictions using correlation. Now we'll talk about the statistics. Mean is the mathematical average, the average we're used to. The median is the middle number, just like the median is in the middle of the road. And the mode is the most common number, just like that a la mode pie is the most common kind of pie. T-tests are a statistical test which is used to compare 2 means to see if they're significantly different. And ANOVAs compare 3 or more means. Nominal scales are scales in surveys that use non-numerical categories such as male or female. Ordinal scales use rank, like first place, second place, third place. Interval scales have meaningful numbers but no absolute 0. And ratio scales have an absolute 0. A reliable research measure gets the same result every time and the same result with every researcher. The results are consistent if they're reliable. A valid measure is measuring the right thing. If our measure measures what it's supposed to, it's valid. Informed consent is part of the ethical process, and it ensures that research participants know what they're getting into. And the IRB, the Institutional Review Board, is the institution that approves research to make sure that it's ethical. That's it for Chapter 2, Research Methods in Psychology of Work. Please reach out to me via email if you have any questions at all. I'm happy to help. We can always book office hours, or I can help you through email. Now that you're done with Chapters 1 and 2, you are ready for your quiz, but don't forget to review the chapter summaries before you take it.